Let's do some exercises from section 3.3 of Anton. So this first one, number 7, says determine if the following planes are parallel. So the solution is to look at the normal vectors of these planes. So the normal vectors are the coefficients on the variables x, y, and z. So in the first case, the normal vector is 4, -1, 2. And in the second case, 7, -3, 4 are the coefficients and therefore the normal vectors. And two planes are parallel if and only if their normal vectors are scalar multiples of each other. So here I've illustrated two planes that look, parallel. And then in each case, then here's the normal vector for this one, and for this one, the normal vector could be here, or another normal vector could be this pointing this way. There's many different normal vectors for any given plane. But in both, the point is that they all point in the same direction or the opposite direction. But either way, all of them are scalar multiples of each other. This one here might be -1 times this or that. And so that's the key idea here, is that planes are parallel if and only if their normal vectors are scalar multiples of each other, because two vectors are scalar multiples if and only if they point in the same direction. Here's an example where two planes are not parallel, and then their normal vectors are not pointing in the same direction, and therefore not scalar multiples of each other. This one points in this one points in that direction, and this one points in a different direction. Okay, so the question boils down to, is there a number k, a scalar, such that k times the first normal vector is equal to the second normal vector? And the way scalar multiplication of vectors works is that the scalar multiplies each component. So k times this vector is 4k times -1 times k, and 2 times k. And so we want this vector equal to that vector. And the way two vectors are equal, if all of their components are equal, component-wise. And so we need 4k, the first component, to equal the first component there. So we need 4k to equal 7. So that forces k to be 7/4. But we also need -k to equal -3, and that forces k to equal to 3. But k can only be a single value. It can't be 7/4, and it can't be this other number 3. And so we know that because there's not a single choice of k, these planes are not parallel. Okay, so that's the answer to this question, is that no, the planes are not parallel. Incidentally, here I've also computed the 2k equals 4, and that forces k to equal 2, which again is different from these numbers here. And so the planes are not parallel. Now let's try number 9, which is the same question, but for a different pair of planes, and maybe this time they turn out to be parallel. Well, okay, so first of all, this plane here, we need to do a little bit of algebra to extract the normal vector from it. We need to move everything to one side of the equation. So now we have 8x, I subtracted off with 2y, so -2y minus 4z, and there was a 5 left over here. Okay, so then the normal vector is the coefficients on the x, y, and z. So 8, -2, and 4 is a normal vector. Again, the normal vector, there are many normal vectors for a given plane, all a scalar multiple of each other. And so, for example, dividing through by 2, we get 4, -1, -2 is also a normal vector for this first plane. Okay, then let's go take the second equation here, move everything to one side of the equation. So we move the -1, the 1/4 y over to the other side by subtracting, and similarly for the 1/2 z. And so the second plane here, its equation is given by this, and so the normal vector is 1, -1/4, 1, -1/2. The coefficients on the x, the y, and the z in that order. And so now that we have the two normal vectors, this one, or I could use this, but I decided to stick with this one, and this normal vector, we have to ask, again, the questions, are these normal vectors scalar multiples of each other, is what the question boils down to. So is there a number k, such that k times this one is equal to the other one? Or I could have done k times this one equals this, but just make a choice. Okay, so again, k times a vector is k times each component of that vector. So I've computed this thing here, and I need to find a k such that k equals 8, negative k over 4 equals negative 2, and negative k over 2 equals negative 4. And this equation here forces k to equal 8. This one also forces k equals 8. So k equals 8 works in all three cases, and so the planes are indeed parallel. Another question is find the equation of the plane that passes through this point here and is normal to this given vector. And that's going back to this equation here, essentially the definition of the normal vector. Okay, so we start with an arbitrary point P in the plane with coordinates x, y, z, and the condition is that the normal vector dot product with the vector from P0 to P is equal to 0. The normal vector is this. The vector from P0 to P is given by subtracting the components of P minus the components of P0, and that's done here. Then negative 2 times this, plus 1 times this, plus negative 1 times all this. It computes the dot product. And simplifying that, we get this. So this is our answer. Next, let's do a question from section 3.1, number 19. And it said, find scalar C1, C2, and C3 such that the following equation is satisfied, namely C1 times this vector plus C2 times this vector plus C3 times this vector is equal to this other vector that they gave us. Now, again, the reason they're asked this question is we're going to see in a later chapter that this is saying that this vector here is in the span of these vectors. In other words, this vector here is a linear combination of these vectors here. So what this equation boils down to is, well, this is a scalar times a vector. So that's multiplying each component of the vector by the scalar. So we have C1 minus C1 and C1 times 0, which is 0. Similarly, we distribute, if you will, the C2s and likewise the C3s, and that equals this, or has to equal this. And then adding three vectors, vector addition is done component-wise. So the first components add together. So C1, 3C2, and 0 is the first component of the sum. The second components added together form this term here. And then finally the last or third components add to this, and that has to equal negative 1, 119. And so two vectors are equal if and only if their components, their respective components are equal. So C1 plus C32 plus 0 has to equal this. So that's what this equation here stands for. Similarly, the second component on this side has to equal the second component here. Therefore, we get this equation. And finally, the third components give rise to this equation. So we have to solve the system of equations, and that's what we learned how to do in chapter 1. Namely, we form the augmented matrix. So the coefficients 1, 3, and 0 are the top line here. The constant there is out here. Similarly, negative 1, 2, and 1 are the second row. And then 0, C1 is equally there. And then 1, C2, and then 4, C3 form the coefficients of the third row. And then the 19 is carried over here. Okay, so next what we have to do is find the reduced row echelon form of this matrix. So we've got a pivot 1 here, so that's great. So next we can turn this negative 1 into a 0 by adding row 1 to row 2. So that's how I got this row. That negative 1 is turned into a 0 is the key point. The 3 and the 2 add to 5. Next, well, it's great that we've already got 0 here, so now we're finished with this first column, and we can move on to the second column. I notice that I've got a pivot 1 here, so let me use that to cancel this 5 and turn it into a 0 by replacing row 2 by adding to it negative 5 times row 3. The negative 5 times 1 added to 5 becomes 0. Negative 5 times 4 is negative 20. Added to 1 becomes negative 19. Negative 5 times 19 is negative 19 times 5. Okay, so I'm at this stage now. I can I guess what I did next is swap row 2 and row 3. So I bring this pivot 1 out up here. And then I'm going to clear out this 3 by using that pivot 1, by replacing row 1 by adding to it -3 times row 2. So -3 times 4 is -12, so that turns into a -12. And then -3 times 19 is -57. Adding it to -1 turns into -58. Okay, so then I've got zeros in the second column except for this pivot 1. So I'm done with the second row. I can move on to the third row. I've got this pivot 1 very conveniently here. I can use it to cancel or to make the 12 disappear or the -12 disappear by replacing row 1 by adding to it 12 times row 3. 12 times 1 is 12, adding it to -12 turns it into a 0. 12 times 5 is 60, adding it to -58 turns into a 2. And then finally I can make this 4 disappear by adding to row 2 -4 times row 3. -4 times 5 is -20, adding it to 19 it gives me -1. And so now this matrix here is in reduced row echelon form, and I can read off the solutions, namely that C1 plus 0 C2 plus 0 3 C3 is equal to 2. In other words, C1 is just equal to 2, C2 is equal to -1, and C3 equals 5. So that's the answer. Now, as a reminder, let me show you how to do this in Sage. So you type CoCalc into Google and get to this page. Okay, let me just click here, and let's just click a new Sage worksheet. Okay, and I want to enter my matrix. Let me call this matrix A, matrix QQ for the rational numbers, and it's going to be a 3 by 4 matrix, so 3, 4, and what the entries were 1, 3, 0, -1 along the first row. Then the second row was -1, 2, 1, 1 along the second row, and then the third row finally was 0, 1, 4, and 19. Okay, and then I hit Shift Enter or hit Run. Now this is going to take probably 30 seconds the first time you try to connect to the server or what have you. Okay, then let's hit see what A is. Okay, it's this matrix here, and then we do A dot reduced row echelon form, hit Shift Enter, and boom, there we get the reduced row echelon form as we found by hand.